our second set of pedagogical lectures by Tom, quantum many-body scars and Hilbert space fragmentation.
Okay, great. Yeah. Hi, everybody. Yeah, thanks for giving me the opportunity to listen to the sound of my own voice for 4 hours.
Thanks for accepting this opportunity.
Yeah, so, I'm going to talk about some, well, I guess, okay, we've been learning about, we learned about what thermalization or equilibration, what those important concepts are, right? From Leo's lectures. And we're in the process of learning from Antonello's lectures about how when you add disorder, this makes it harder or perhaps even impossible to equilibrate or thermalize. And in these, 2 or 4 lectures, depending on how you count, I'm going to talk about some other mechanisms, just kind of a grab bag of mechanisms that can also help prevent thermalization, and those are scars and Hilbert space fragmentation. Apologies for already abbreviating things. So today I'm going to primarily talk about scars, and I'll consider myself lucky if I get to the end of this. And then in that event on Wednesday, I'll talk about Hilbert space fragmentation. But yeah, please stop me with questions and things as we go, because as much as I do like the sound of my own voice, it's for you, not me, that this is happening. So yeah, please just stop me whenever. So just to remind ourselves, so I wrote this up here because the theory of everything, I was being a little sarcastic, but so the everything isolated Hamiltonian, right? Those are my 2 things. So we learned how, when you take time to infinity here, what are the ingredients, right? You've got 3 ingredients here. There's phases, right? These phases are oscillating in time, unless they're not. I'll talk about that in a sec. And then you've got these overlaps. So this is telling you something about the distribution of energy in the initial state. And then you've got these matrix elements, right? And ETH kind of tells you things, right? About, for example, those matrix elements, right? It tells you something about how they should behave. And then also there's things like spectral statistics, right? That tell you something about this guy maybe won't be too small, right? Which is a good thing. So I guess what I wanted to say before getting into what scars are is I wanted to talk about what is the obstruction, or what can be the obstructions of getting from this formula, which is always true, to the formula O of t equals trace e to the minus beta h O as t goes to infinity, right? So what are the ways that this can not work, right? So there's a few ways. So how to avoid, would you call it thermalization or equilibration, Leo? Yeah, good. That's what I was going to say, but I wanted to check. So if you look at this formula, you can go ahead and think okay, well, what were the ways that it's supposed to work? And then, just assume that none of those things happen. So one thing is that you can have resonances. So for example, basically what that means is that there exist, N and M, such that En minus Em is equal to 0, and the matrix element is non-zero, right? So that's something that you try to avoid. For example, in a situation where you have level repulsion, then you can be reasonably confident that this doesn't happen, right? Another thing that can be kind of problematic, right, for thermalization is if you have a structured energy distribution. So what does that mean? It has something to do with these overlaps. Okay, so the overlaps in a nice generic scenario, if you draw them as a function of energy, look like. And then one thing that you'll learn about me is that I'm really bad at drawing and sketching. So my apologies. But this is meant to be a Gaussian, okay, roughly. And then this width of this Gaussian is of order root n, roughly, if your psi naught, like if your initial state is reasonable, okay? And what does reasonable mean? It means that it's short range correlated, like nothing special happening. But, you know, if you have, like, for example, a disordered system, right, you can make the same plot, and then what do you have? You basically have some, it's very tightly peaked around some energy, right? So this is kind of, you know, if your system is localized, then when you make this plot, your initial state in some real space basis, say, when you look at its projection onto eigenstates, actually, you only need to kind of dress this guy a little bit, and then you get this peak, right? So that's another way that you can kind of avoid thermalizing to a standard sort of distribution. And then the other thing is that you can have structured matrix elements. So, you know, maybe these off-diagonal matrix elements for some choice of states, EM, right, are not exponentially small. Some choice of states, eigenstates now, I'm not talking about initial state, I'm talking about eigenstates, and I'm talking about a special choice of operator. So maybe your system has some special eigenstates, and maybe if you choose to look at a particular observable that's just right, this is not possible. Like the off-diagonal matrix elements are going to be of order 1, right? So both of these mechanisms, like scars and Hilbert space fragmentation, are giving us like different routes to like violate one or more of these things. So that's kind of why. So I'll leave the, you know, the theory of everything over there probably, and almost certainly erase this thing because I won't have enough space. But I wanted to give you a sense of where things are going. But yeah, so the question is basically how can you avoid these things? And what I'm going to basically be doing this whole time is giving you examples of how that can happen. Okay. With that, we don't need this anymore. I have it here anyway. Okay. All right, so I'll start with quantum antibody scars. That's what QMBS stands for. And, you know, so there's review articles on this. There's 3 of them. Maybe at least. There's at least 3. So there's this one that Zlatko was involved in from 2021. There's Sanjay's. And Nicolas and Andres. And then there's this one, which I was involved in. So you can guess which one I'm going to be following the most closely. But they're all very good, and they all give you kind of a different perspective, because there's a lot of different ways to look at this topic. So it's actually useful to look and see these different perspectives. But everybody kind of agrees that, you know, quantum antibody scars as an observable phenomenon were first seen experimentally, right? So there's this paper Nature, right? From Misha Lukin's group, where basically they had this very nice quantum simulator. I'll try to draw it. So these little guys are atoms, not to scale, trapped in optical tweezers, okay? And the nice thing about this platform is that you can move them around. You can control how strongly they interact. We know roughly what the Hamiltonian is, right? I won't get into the atomic physics, but basically these atoms are kind of trapped and they're driven in such a way that they're kind of limited to these two states, each one. So there's the ground state, atomic ground state. And then there's some Rydberg state, which you can choose, you know. You can choose the like principal quantum number, you can choose the orbital character of it. And you know, depending on what you want to do, I think they use like principal quantum number 70, for example, and there's a reason for that that I'll probably say something about. But for our purposes, I just want to define the Hilbert space for you that we'll be dealing with. So to describe this system, let's say that this is like atom I, and this is atom J. There's a local basis where you map the ground state to 0 and the Rydberg state to 1. My mouth and my hands are like not connected. I don't know why. I encounter this problem over and over again. Good. Okay, so there's operators, these occupation numbers, which are essentially projectors onto this excited state. So 0 on site I is annihilated by this occupation number operator. And then 1 is an eigenstate. Okay. And then you can define some operators. You can define Pauli operators essentially. So I'll call xi is you know, the Pauli x operator. And this is basically Rydberg ground on site I plus ground Rydberg on site I. And then of course you can write it in zeros and ones if you want. And then there's also a Pauli z operator that you can define, which I'm going to be annoying to you and define it the opposite way that Nielsen and Chuang does. So I'm sorry. So 0 maps to -1 and 1 maps to 1. Okay. Why am I going to do that? Because I'm not going to use Zlatko notation that we learned about last week. I'm going to use zeros and ones. So with apologies. Okay, great. So this is kind of the setup. And this setup has a very nice Hamiltonian, or it quantum simulates a nice Hamiltonian, which is so I'll say I less than J, Jij, Ni, and J. Talk about that in a sec. And then you can have your detuning if you want. So what are these things? So this is a two-body interaction between these densities. But if you wanted, you could take this guy, invert it, and plug it in here. And what you would see is basically there's a ZZ interaction, like an Ising interaction between atoms I and J. And then there's also an on-site field as well, because there's going to be like a cross term that comes out. So you have ZZs and Zs. And then this guy is going to give you a Z. Okay. And then this guy's just X. So really this thing is a mixed field Ising model. And some people call it mixed or tilted field. I'll probably capitalize Ising. So this is like, we have the theory of everything and we have the standard model. So this is like the standard model of thermalization pretty much. But it's not quite. Why? So this guy, for example, so Jij goes like some constant C. Sometimes people call it C6 because it's Rij to the 6, maybe. Is that why people call it C6? Yeah, good. Phew. Great. So what is this? So this is actually a cool thing. So what happens is when you excite the atom up to its Rydberg state, it gets bigger, right? That's no surprise. And when it gets bigger, it's more polarizable. And when you have two atoms that are excited, they're both more polarizable. They're sort of dipolar, but it's like a higher order van der Waals interaction. So this is van der Waals. It's not super long ranged, right? We talked about, right? It's actually quite short range in the grand scheme of things. But the whole point is that it also depends on the R's, right? And the nice thing is that, so Rij, what's Rij? You can probably guess. But these guys are separated by a distance. Rij. And the nice thing is that you can move these things around. They don't have to be, it doesn't have to be 1D, doesn't have to be 2D, doesn't even have to be a lattice. It could be a graph, right? And how strongly the atoms interact is just determined by their proximity. So you can decide if you want the atoms to interact strongly or weakly, and that turns out to be useful. And then what are these other terms? Well, so you have a ground state and a Rydberg state, and then this is like some detuning between the transitions. So that gives you a little bit of like a phase offset, if you like. So that's what delta is. And this is essentially going to, this guy combined with the cross terms that you get from here sets your field, your Z field, okay? And then this is the Rabi frequency of the ground Rydberg drive that basically is controlling the rate of transitions between these things, okay? Okay. Any questions about the setup? Great. I was going to ask, am I going too slow? But I don't think I have much. I could go slower, but I don't think I could go faster. Good. Okay, so this is great. And now I'm going to go on a little bit of a digression, but it's not really a digression because it's just background for what comes next. So there's an interesting regime here. There's other interesting regimes, but there's this sort of Rydberg blockade regime. Which is basically, you should think of it as, small delta and omega regime. But, and I say this because your detuning can be positive or negative, and then that's, sometimes important. But how small is, of course, the whole game, right? So as an example, nearest neighbor blockade. So this is when Vi, I plus 2. So now I'm in 1D. The whole talk pretty much is going to be in 1D. Is much, much less than omega and delta. V is a typo. V is what I wrote in my notes, but it's J. Thank you. Very good. See, this is what I need. I need, give and take. It's good. Good. So this is basically like, you can sort of, you can't control how fast the interaction falls off, but you can control how far apart the atoms are. And then there are these sweet spots where your omega and delta are kind of between the interactions of different ranges. Okay, so this is like your nearest neighbor interaction is bigger. I put a lot bigger, but in reality, it's not, that's sort of in the eye of the beholder. But the mathematical limit is the nearest neighbor interaction is much bigger than omega and delta is much bigger than the second neighbor interaction. So what people do in this limit is they just assume that the second neighbor interaction is gone. This is strictly speaking not true. It's an approximation, okay? But what happens, right? What does this mean? So like now just imagine that this is nearest neighbor only, right? And then the coupling j I plus 1 is infinite, okay? So what does that mean? It means that if you consider two sites, nearest neighbor sites, this state 1, 1 has much higher energy than 0, 0, 0, 1, and 1, 0. And this is, I'm assuming like delta is equal to 0 and omega is like almost 0. Okay, so if you do this, it basically is taking these nearest neighbor excited pairs of atoms and their energy just goes to infinity. They're separated in reality by a gap to these other states. Right. So what does that mean? It means that if you have like a chain of atoms and you have, say, 0, 0, 0, like this, you can apply an X. Maybe I should, Zlatko wanted me to do like a multimedia presentation, and I think this is going to be the best I can do. So you flip this site. It's all the same medium though, so it's a bit of a failure, but whatever. So you can flip a site here, right? And this flip costs no energy, right? If delta is 0, and then this thing is infinite. But if one of your neighbors is excited, right? So let's say 0, 0, 1, right? So if I flip the middle guy again, I would get 0, 1, 1. But now, like Edward marker hands over here. Nobody? Okay. So yeah, you flip this spin, and then you get 1, 1, okay? And the point is that this transition is going to be heavily energetically disfavored, okay? Very good. So we say that the middle site is blockaded, all right? Any questions so far? Good. That's my goal. Just adiabatically, I'm just going to adiabatically go without exciting any questions. That's my goal. Good. Okay, so one thing that you can do when you get this, right, is say, okay, now I want to study a many-body system, right, with this, where, 1, 1, anytime that you have two ones next to each other, that configuration has a much higher energy than the ones that don't have nearest neighbor pairs of ones. And so what people will often do is just project configurations with two nearest neighbor ones out of the Hilbert space. So let me give you some examples. This is an example within an example. It's a nested example. And that's going to be pretty much the story of these lectures. Maybe I'll indicate that it's within. Okay, so example is L equals 2 atoms, okay? We just kind of talked about it, but like if you just say, okay, configurations with 1, 1 are not allowed. So 0, 1, 1, 0, 0, 0 are allowed, and 1, 1 is not allowed, right? So that means that the dimension of the Hilbert space for L equals 2, that's what this symbol means, is 3. Okay? Which is pretty good, because like 2 squared is 4, so you've already got one less state. That's nice. That's why people do this. For L equals 3, well, you can take this and add one more site. So let's start with 0 and 1. Okay? Now I'm going to add a third site. What can I put here? I have to put a 0. Yeah. I have no choice. Good. So then I can do the same thing with each of these 3 configuration. So if I start with 1, 0, this guy's 0, so I can actually have 0 or a 1. Sorry? Depending on the boundary condition. So let's say OBC, because that's where the counting is easier. This one, doesn't matter. Good. The minimal example where boundary conditions matter. Good. All right. Or, right, 0, 0, you can also add 0 or 1. So then D3 is 5, right? And then this means if you keep doing this, what happens? Well, this will be an exercise for you. Exercise. I can't, because this is an example. Exercise. So show that the Hilbert space on L atoms is equal to FL plus 2, where this is the L plus 2 Fibonacci number. Okay, so that's, 1, 1, 2, 3, 5, 8, etc. Okay. So this is something you can do, but you can kind of get a sense, right? Because you take the one from before, add one more site, and then you get this kind of branching, and you can actually, if you think about it enough, you'll see that there's a recursion relation. Okay. So for that reason, people call this the Fibonacci Hilbert space sometimes. Okay. And the point is that if you take this Rydberg atom system and you choose the distance between the atoms just right, you can set things up so that this is almost satisfied. And then you can, for that reason, if you initialize in a configuration that is in this Hilbert space, you'll never, on the relevant timescale of the experiment, you're never going to be able to see that you leave. Okay. Good. So that's what they did. Well, one of the things, they did a lot of things in this paper, but one of the things that they did was they did a quantum quench in this regime. Okay. So let me tell you what they did. Okay. And this has kind of been brought up already and discussed. So let me tell you what they did and what they saw. Okay. So what they did was they prepared the so-called nail state. So this is 0, 1, just repeating forever. They could have prepared the other one. Maybe they did prepare the other one because I don't remember which one they used. But yeah, so you prepare one of these alternating ones. And as we learned from one of the talks last week, from Evgeny's talk, right? This is the one that has the most excited atoms that you could pack into the system. So as an exercise for you, again, I'm just going to keep dropping these because if you get bored, you can always do exercises. Okay, so they prepare this state, and I want to ask how? How do you think they prepared it? Okay, think about the Hamiltonian that was there and that I erased, helpfully. And then think about if you wanted to prepare this state using the control that you have over those parameters, how would you do it? All right. I'm not going to stick around, but it's useful to think about like how do they actually do that? Okay. Okay. Then what did they do? So then they did a quench. So they did whatever they do to prepare this thing, which you can figure out. And the quench that they do is they set delta equal to 0. and turned on omega in the blockade regime. So what that means is they basically set this detuning to 0, and then they turn on their laser that's driving everybody, and they just let it evolve. Okay, and effectively what this is doing is evolving under this PXP Hamiltonian, and it's called PXP because the Hamiltonian is PXP, where PI is 1 minus NI. There was a time when referees, if you did this, they would be like, define the acronym, please. And it's not. Yeah. And this is actually, there's a paper from back in the day by Benli, Gupta, and Sachdev. 2004. Excellent. So they were actually looking at ground state physics of this and already seeing cool stuff. So there we go. So they're evolving under this Hamiltonian, which, okay, why is it written this way? It's written this way because basically you take your whole Ising thing. The first term is automatically 0, the NN, because you just restrict to configurations for which that term is 0. And then there's no detuning, so there's no Z term here. And then you're just left with this thing, which has been now dressed with projectors because the projectors are telling you when it's not okay to flip a spin. And it's not okay to flip a spin if it's not okay to flip spin I if either of its neighbors is excited. Okay. And then they measured a bunch of things, but really like the things that they measured could all be reconstructed from measuring basically the occupation as a function of time. Okay, yeah. Yeah, so the first term was, so there was, I less than J. For some reason, I chose to call it Jij. Don't ask me why. V is much more natural. No. So this thing is the first term. And then, remember, N is just basically telling you whether it's 0 or 1. And then you're projecting, you're restricting to configurations where you never have two ones next to each other. That's the only time that this term is, I mean, if this was really nearest neighbor, so let's just call it sum over I, and then this is I plus 1, right? The only way that this term can be non-zero is in a configuration where you have two ones next to each other. So you've just turned it off, essentially, by your choice of energy scales. Make sense? Or? That's right. This is sort of an effective model for what's going on that people like because of this thing. People like it because you throw out a lot of configurations this way, so you can do like 30-something spins instead of 20 spins.
Or the space of this leaf in this Fibonacci space.
Exactly. Yeah, and that is set in a preview of next time by your choice of initial state. So your initial state didn't have any 1-1s in it. It's this guy, 0, 1, 0, 1, 0, 1 forever. And because this thing is completely, like once you initialize yourself in this sector, you can't get out to a good approximation. If you wait long enough, you can get out. But the experiment doesn't go that long. Yeah. Cool. Any other questions? Again, it's for you, it's not for me. So don't be shy. Good. Okay. So what do? They measure this thing, and then now my incapacity to, or whatever the word is, to draw comes back to me. So this is time. And then I'm going to draw occupation number. And what do you see? You see, well, one of these guys is oscillating like this. And then another guy is oscillating like this. So this is, say, Ni of t for some choice of I. And then this is Ni plus 1 of t. So basically what you, this is I mean, of order the number of oscillations they could see in the experiment. They couldn't go very far. But essentially, you see this staggered pattern. Like anytime you look at the spins, if one is more likely to be up, then the one next to it is more likely to be down. And this pattern kind of persists longer than you would expect. Okay. And you look at this and you say, okay, probably it's helpful actually for me to write what my scale is here, right? So this is, look at this. This is the best I've ever done this. And I am already, this point should be here. These were good. So 2 out of 3 ain't bad. But anyway, this should be 1/2. And then this should be 1. So your density is oscillating in this pattern. And you look at this and you say, well, there's many ways that I could produce this pattern, right? I could just have a bunch of spins oscillating in a magnetic field, right? So what's the big deal? Well, one thing is that the frequency of these oscillations is omega over something of order 1. They estimated like 1.33, but you know. Why is that interesting? So if you had just omega, you'd say, okay, this is Rabi oscillations. You've taken 40 minutes to talk about this, Tom. Why? But you know, with this 1.33, basically that tells you that these aren't, it's not a single body thing. The interactions are playing a role. And then it's been, you know, surprisingly hard to understand this phenomenon, I would say. So, okay, that's the experiment. And then very shortly after, Zlatko and collaborators showed us, you know, sort of the, you know, why. I mean, it's really still phenomenology, essentially, but, you know, there's a reason that you get this, and it's not Rabi oscillations. So if you go back to that thing I drew at the beginning, what does it look like for this PXP model? They're restricting to this PXP model, but you could do it for the original Ising as well, and you would see the same picture, pretty much. It would be a little different, but they see something like this. And Yevgeny showed this on a log scale, but I'm showing this on a linear scale. So when you plot it on a linear scale, it looks something like this. You see these spikes. And you get these, you know, the sort of things that people call quantum many-body scar states are these states that have the most overlap with this snail state. But there's also a bunch of other states nearby in energy that also have kind of enhanced overlap. That's actually one of the things that makes this a little bit challenging to understand, is like if you want to explain this, right, you can explain these, but then you have to explain these too. And it's not necessarily the easiest thing to do. But okay, so this is not a Gaussian, right? For this initial state, it's got some structure, and there's this energy gap, which is, you know, of order this frequency. So the oscillation frequency is due to basically this frequency comb that you get when you project onto the initial state. Okay, so these states are called quantum many-body scar states. And they sort of, people, you can define like what is meant by this thing. I don't know. I'm going to say that I'm going to highlight three things, okay, that are important about them. One is that they have high overlap with the nail state. Okay. And what that means is that they kind of dominate the dynamics, that the like when you plug that into the theory of everything, it's not as many eigenstates that participate in the dynamics as you would get for a generic initial state. So this is already one thing that's kind of unusual, because usually you would just say, okay, it should be a Gaussian centered around the average energy of the initial state, but that's not what we see here. We see this spiky thing centered around the average energy of the initial state. The other thing is that they have nearly constant energy spacing. So actually, even in the PXP model, it's not the case that the energy difference is exactly the same between any two of these, any two consecutive ones. It changes a little bit, that's another thing. And then, actually this, so if all of this was perfect, you would actually be able to see like, essentially if you look at this return probability that we heard about today, so you take psi of t and you overlap it with psi of 0. What you would get if psi 0 only overlapped this set of states and the energy spacing was constant, you would get basically, oh yeah, I wanted to give you some notation for these. So I call these things Sn, or that's the, whatever. And here n actually goes from 0 to L. So there's L plus one of them. So then what you would get is sum over n equals 0 to L. There would be your overlaps squared. And then you would get something that's like, e to the minus I. I guess I'm looking at the overlap, so it'd be 2 n omega t, where now, oh, maybe I won't call this omega because it's not the Rabi frequency. It's the frequency spacing, okay? So you would get something that's actually, the state is really coming back to itself periodically in time. Now, what you really see if you look at this numerically is, due to the unequal spacing and due to the fact that there's overlap with other states that are also going to contribute to some dephasing, you see these revivals kind of decay. So if I plot this f as a function of time, you sort of see something that decays over time. Okay. All right. And then the third thing that is special about these, and then I guess maybe I'll take the suggested break. So yeah, the third thing is that these states have subvolume law entanglement entropy. So if you plot, for example, the von Neumann entropy, which would be minus trace rho of subsystem A log rho of subsystem A as a function of energy. If you were projecting into like one symmetry sector of an ETH obeying system, you would get sort of a thin band of, you get this like Star Trek thing with a maximum in the middle. But what you see here is actually there's, these, how many did I draw? 5. So you get these low-lying states, low entanglement states. You also get actually a bunch of other stuff here that are a little bit below kind of where you would expect, which again, I don't think that it's exactly super well understood why this happens. But what you can show is that if you plot this thing for these, so for say this guy, as a function of log of system size, you get sort of almost a straight line. So something that's like a, so you get this log entanglement as like a third feature. So after we all have a coffee, I will show one model. There's actually many models, but I'll show one model where all of this stuff is exact. Okay, so everything that I've shown so far is approximate, and it's not just approximate because like the blockade itself is an approximation. Like even when you make the blockade a hard constraint, it's still approximate. But that made people kind of think about models where maybe this can happen exactly. So I'll tell you about one such model after the break. Yeah.
Yeah, just for clarity, when you say that the scarce states go to L, this is the system size or just a random number?
Sorry, what do you mean go to L? Oh, you mean this?
Yeah, yeah.
Oh yeah, L is the system size. So there's exactly system size plus one of them.
Really?
Yep.
Okay.
Yeah.
Okay, so you can predict how many.
Yeah, there's exactly L plus one of them. Yep. Any system size, you can do it yourself. You'll find exactly L plus one of them. Yep.
And there's some reason for the condition for constant energy spacing. So is there a mechanism of?
So I'm going to tell you about a mechanism next time, but whether it's the mechanism that operates in this experiment is not settled. And that's the thing that makes this. You can come up actually with multiple ways of seeing this phenomenology come out exactly, and we don't know which one is right.
This is somewhat particular in this sense. So.
Yeah, so this, we don't, I'm going to stress, like I was told that maybe you said conveying optimism. Was that what you said at lunch? Is like, so we don't know, we don't understand this model.
This is optimism or pessimism? Is optimism because
That's for you. That's for you to decide.
Okay, okay.
You can decide.
No, it's optimism because it means that
It's
there is something
optimism
to
because
do.
there's a mystery.
Okay, okay, yeah.
But maybe pessimism because, like, look at the number of papers that have been written about it.
Yeah.
But, yeah.
Perhaps a comment. Do we agree that condition 3 is somehow necessary?
No.
No, wait. I didn't
it's not
finish.
Necessary. Sorry, yeah.
I didn't finish. Because, I mean, you are saying that you have a state, psi 0, that is a zero entanglement, is a product state, that can be essentially deconstructed by a extensive superposition of states.
Yeah.
If these states were high entanglement, it would be highly likely that psi 0 will be high entanglement as well.
Sure.
So the fact that these SN are small entanglement is necessary in order to...
It's surprising. You can add up a bunch of volume law states and get a product state.
But you need more than an extensive number, I would say. You need probably an exponential number of them to make a product state.
Sure. Yeah, exactly.
So you agree on that?
Yeah, that's right. Totally.
Okay.
Yes. Yeah. And I will say none of these things is like, so I'm showing you these 3 things, and then I'll show you how these 3 things happen. But people have written papers about scars where like
you have just one,
or where you have just one, or where you have volume law scar state. I mean, all of these things can be played with. I didn't write definition quantum many-body scars because it's not I don't think that there's really a good.
But let's say certainly 1 and 2 are necessary both in order to have the revivals.
Yeah,
If you violate one
for sure.
or two,
Yeah.
the revivals are gone.
You need these things to get revivals for
And
sure.
I would say that 3 is to ensure that the state that showed the revival is not a horrible crocodile, but is a
Yeah.
well-behaved state.
So what you want is you want atypical states.
Yeah.
You're just saying there's atypical states. And there's atypical states in all kinds of models. It's not like this was the first time people found atypical states. The thing that was surprising was that there's these atypical states and then there's multiple of them and like they have this structure and people want to understand, right? Yeah, but they're particular, I would say that they're atypical states that can be somehow expressed exactly, but then I would be ruling out the PXP.
Yeah.
You know, so anytime, yeah, so, you know, it's kind of it's a tricky business. Yeah.
This plot of the entropy versus
Yep.
the energy, each point is a random state.
Is an eigenstate, yeah, an energy eigenstate. So basically I take my big matrix and I diagonalize it, and for each state I compute the von Neumann entanglement entropy, and then I make a scatter plot of these. And if you do this for an ETH obeying system, you know, you get something like what you learn in StatMech, which is, you know, entropy versus temperature, if you like, you know. So that you get basically something that has this form, with infinite temperature being where the slope is 0 in the middle of the spectrum. Are you?
I'm kind of confused because there the psi 0
Yep.
was like the superposition of many
Well, it's sort of a
States.
superposition of scar states, yeah. It's sort, you know, again, this is all approximate, but yeah, it's a superposition of some eigenstates. Yeah, but that's the point. So psi 0 is a product state, and then you look at its overlap with all of the eigenstates, and what you see is that actually this state, if you wrote it, if you expressed it in the eigenbasis of the Hamiltonian, it would be dominated by these
A few of them.
5, yeah,
Not like that.
yeah.
And then these few are also the ones that are special in the.
These are the special ones, and then they have this property. Yeah, that's right. Yeah. Oh, well, yeah, let's privilege the students.
Thank you.
Or, you know.
So this should be a quick question. What kind of bipartition are we looking at here?
Yeah, that's a great question. So this is just, you know, the standard bipartition where you would just say that subsystem A is like these ones. But I think in this particular one, I think it doesn't necessarily matter. For a contiguous bipartition, I think, well, yeah, no, if you do stuff like this, you know, why would anybody do that? Actually, yeah, we have a paper. We have a paper. I say that because we have a paper where we did something like this. Yeah. No. But I would say any contiguous bipartition, probably the scaling is log for these ones. Certainly that would be true for Dickey states, which I will talk about later, and which these are that they're not really Dickey states, but maybe they're similar in some respects. Yeah.
Thank you.
Yeah, no problem.
What?
Anybody else?
I'll ask one.
Sure. Yeah, sure.
I mean, as I understand it, if you look at the square average, there will be an exponentially large in L number of eigenstates, and there's an order L number of eigenstates which form the star states, right? So they're a set of measures 0.
Yeah.
And you're basically assuming they're decoupled from the other eigenstates in this kind of
Yeah,
approximation.
exactly. That's the kind of, it appears to be that is what this thing wants to be.
Okay, gotcha. And
Yeah.
From an experimental point of view, how many of these scar-like states do they see? Is it significant? They see.
They'll see linear. I mean, I guess
They
it
could do
depends
up
what you
to
mean
L
by
equals-
C.
They could do up to L equals 1.
Up to L equals, I think they've done it like in 2D, they've done it 256 atoms. It's been taken very far, but in the original paper, it was like 50 something
Okay.
atoms.
They're 51 scars.
Yeah.
Or whatever.
It was like but you know, I think they can do like probably as many sites as you want now.
Okay.
Yeah. Any other questions? Whoops. Yeah.
What is the vision behind that scars?
That's maybe the intuition. That maybe there. I don't know if intuition is the right word. If it sort of, but
Oh.
yeah, there's.
Or how to
It's
see.
probably intuition. So there are older examples of this where you can understand why, and I don't. But that's going to be next. That's after coffee. You guys want to learn about Hilbert space fragmentation? I mean, this is what I do. This is what, like I said, I wasn't joking when I said adiabatically because. So good. Okay. Yeah. I'm fine to wait. Good. Yeah. I'm just going to write something before I start talking because we've established that it's difficult for me to do both at once. Okay. Hi. So, great. So we're gonna now, so, okay, we concluded with like, we have these states, there's L plus one of them. They have high overlap with a low entanglement state, namely in this case, a product state, the nail state. They have a nearly equal energy spacing, and they have entanglement that grows like log of system size. And then the question is, are there models that where all of these features happen exactly? And there's multiple. There's ones that came before this one. I mean, you know, but again, I'm biased. So this is talking about what I know. But you know, the nice thing about this model, to the extent that people talk about it or like it, is that it has a very small number of terms. The other ones have more terms, and that's pretty much all she wrote, I think. There's one or so there's another example from you know, Mudgalia, Regnault, Bernavig, Stefan Rachel was on the first paper in the AKLT model, which is another. This is actually a spin one model, and I'm going to talk about that. Actually, is somewhat related to this example, but again, this is just the easiest to explain probably. So okay. This is the spin 1 XY model. I'm doing it in 1D, but actually, I mean, all of this discussion you can do on any bipartite graph, it turns out. So nothing that I'm going to say is like special to 1D. And then, you know, I'll probably write down the spin 1 matrices just so you know that it's not spin 1/2. Okay, so diagonal, right? And then let me just do like S plus. So I just want to emphasize that, you know, it is spin 1. So this is SZI, S plus I. S minus is going to be the Hermitian conjugate of that. So, okay. Right. And, you know, yeah, you can also write this as like SX plus ISY. And you can write this as SX minus ISY. And this marker is screaming. Wants me to put it out of its misery. So good. And then I'm going to call my local basis plus minus. So SZ acting on plus minus is plus or minus 1 times plus minus, and then SZ acting on 0 is 0. Very good. And I'm going to assume periodic boundary conditions, but who cares? Good. Okay. So this is also a nice model because it has other states that you can write down that are not special. And I think it is interesting to like talk about like what's special about scars versus what's not special. So there are exact states that you can write down for this model that are in the middle of the spectrum, okay? But they're not special. So there's eigenstates that are dictated by symmetry. And these are not special. So unspecial states, which I know is why we're all here, because we want to learn about states that aren't special. So this guy has a U1 symmetry. And with periodic boundary conditions, there's also translation. And what that means is that the polarized states, so that, for example, U1 symmetry, that means that the states, I'm going to call this omega no relation to the Rydberg omega, but there are these polarized states, right? Basically tensor product over I of minus on site I, and tensor product over I of plus on site I. Okay? And these states are not special. They're not special. Why are they not special? Well, they're sort of special. But any model with U1 symmetry is going to have states like this that are product states that are living in the spectrum somewhere. And it's simply because this is the only state with magnetization minus L. This is the only state with SZ equals minus L. This is the only state with SZ equals plus L. So you have a U1 symmetry, you're going to have a state like this. Marker Monte Carlo. I'm just going to pick a new one and see if it works better. So these are going to be here. They're going to be in your spectrum no matter what, okay? So that's just U1. But then if you have translation symmetry, there's also excitations on top of this that are going to be there as well, okay? So you can write down these, you could call them magnon states. So magnon is just like a spin flip on top of a polarized state, okay? So if I have something that's like locally looks like the vacuum, and then I flip the spin, say, up or down, both ways I get 0, right? So this is a magnon on site R, okay? All right. Now, how many states are there? How many of these are there, right? There's exactly L states. And let's say that you start on top of, this guy. Actually, it doesn't matter. I'll just write it down. Because basically, yeah, there's, with magnetization, and magnetization is what? M equals sum over I SZI equals plus or minus L plus or minus 1, or sorry, L minus 1. Okay, so what does that mean? It's just like I have L spins and I can flip one of them. Sure, there's L of those states, right? These are localized. But if I have translation symmetry, that means that, for example, I can define a state plus K, which is just a plane wave of these guys. Nothing special. So sum over R equals, sorry, I feel like I'm really like being mean to these states, but they're not special. So e to the minus I k r, s plus r acting on omega, you can show, I'm not going to show, exercise. Show that these are eigenstates with energy Ek equals 2 cos k, your plane waves, okay? Again, nothing special about this. This is 100% from symmetry. But, you know, if you did this entanglement plot and you like looked at all of your, well, if you did this entanglement plot and you looked at all of your states, you would just see like dots everywhere. But, you know, yeah, these are going to be somewhere in your spectrum and you can write them down. They won't necessarily be low energy states, right? So these guys have energy 0, for example, which is in exactly the middle of the spectrum here, but that doesn't matter. You have to look at the spectrum in each symmetry sector, okay? Again, this is the only state in its symmetry sector because this plus means that, you know, I'm saying, okay, plus, or sorry, this guy would have magnetization minus L plus 1, right? So this guy has a fixed magnetization, and it has a fixed momentum quantum number. And what's K? Sorry. 2 pi over L times P. P equals 0 to L minus 1. Okay. So it's the only state with that magnetization and that momentum. Okay. Not special. All right. Any questions about that? I just want to say this because later there's going to be a symmetry and or an algebra that's suggestive of a symmetry, and then we're going to want to ask, like, are the states that we find here really special? And for some definition of special, they end up being special. So good, but no questions about this. I just wanted to make sure that that's clear, that we're not just saying that, like, just because you can write down eigenstates and the energy is somewhere in the middle of the spectrum, that doesn't mean that these are special states on its own. There are even low entanglement states. I mean, again, but not special. Okay. I think we know this, right? Yeah. I mean, it's our everyday life. All, you know, the universe is a pure state. So this is our, right? I mean, well, I don't know. Anyway. Good. Good. All right. So probably we want to know, like, are there other states that are special? So I talked about what a magnon is. So a magnon, for example, is like minus dot 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 minus 0 minus dot dot dot, right? So this is a magnon. So there's something called like a bimagnon tower of states. And I'll say tower of states. Okay. What's that? Well, instead of, this is you raise the spin once, but maybe you raise the spin twice. So this is a bimagnon. So this is a state which, you know, you raise the spin up twice, and now this is also an excitation. Okay. But we'll talk about what happens to it. So consider the states. Suggestively named. So I'll call them SN because these turn out to be scar states. I'll give them a little gold star saying that they came from this model. I'll give them a little normalization because it would be a pity if they weren't normalized. Okay. So what is this? Well, okay, it's a state, it's normalized. There's the same vacuum that we put the magnons on top of. And then there's this operator J plus. Now, what is J plus? Well, I said that they were double spin flips, right? So sum over R, S plus squared R. And then there's a minus 1 to the R that I'll put here. That turns out to be important. And I'll even tell you what the normalization is, although that's thoroughly unimportant. So it's just some factorials and stuff. Yeah.
That I'm raising the spin price on given site as opposed to saying.
Oh, have you read Appendix F of this master? No, we actually, there are states that are like that. Yeah.
They don't couple to do.
Yeah, but that's actually there's actually more than one special tower of states in this model. And that's actually, if you raise them on neighboring sites, that's actually also something special. They turn out to only be present if you have periodic, or like only, I think it's just periodic, but yeah. And you'll see why it's special to raise twice when I prove that these are eigenstates. Yeah.
States that David is talking about?
Bond by magnons. Of course. Why? So yeah, you raise twice on one site. So this is a site bimagnon. And then if you do S plus I plus 1, that's a bimagnon that lives on the bonds. Yeah. Very good. Any other question? Okay, so there's something special. I showed you a band, right? There was a band of magnons, right? What's this guy? This is e to the minus I pi r. So this guy actually, these are bimagnons with momentum pi. Why not momentum something else? I'll show you. The claim, but the claim is that if this was any other momentum, they wouldn't be eigenstates, and you'll see why. You'll see why. For a while, I was calling this pi magic in my talks, just for fun. Yeah, but you see pi magic everywhere. If you just need to know where to look. Okay, good. So my claim is that these are quasi-particles that are stable. Okay, so what happens with these magnons is I showed you the one magnon states. If you plug in an extra magnon on top of one of those, you'll find that the resulting state is not an eigenstate. You just hit the Hamiltonian onto that state, and then you'll see it's just, you can write down a set of two magnon states, that's fine. That's your right, you know, as a human, human right. But there's, you know, we say that there's scattering. We say that there's scattering. And what that means is that what you get out is going to be a superposition of two magnon states at different, you know, I mean, they're just going to be, yeah, it's going to be a superposition of two magnon states and probably some other crap. Some other crap. So this is special because we're gonna see that I can put any number of these, not just one, not just two, but any number. Okay, and then you'll see why does it stop at L? When you do this L times, you end up in the state that's all plus. So that's the other vacuum that you can make magnons on top of. So any number of these is stable. Okay. That's my claim. And to show that, I'm going to show that H, this guy, acting on Sn is equal to 0 for all. And so these are actually annihilated by this Hamiltonian. Any questions before I begin? Okay, so what do these states look like? If you want to, right? So these things are proportional to j plus to the n acting on omega, right? And if you expand this, this is the same thing as sum over a bunch of r's equals 0 to L of, and then there's a phase factor, -1 to the -1 to the -1. Sorry, that's not what I meant. It's not what I meant at all. Oh, geez. Okay, good. So sum over r of r sub k. So sum over r equals 1 to k, 1 to n, sorry. It's k. I can't read my own handwriting. K equals 1 to n, because there's n magnons. Rk, okay? So this is think about it. Every time you put in a magnon, you're getting a factor of e to the I pi times the coordinate of that magnon. So then you just sum over the coordinates and exponentiate. Okay. And then s plus r1 squared dot 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 s plus r n squared, all acting on omega. Okay, so you just sum over everywhere that you could put these magnons. Just sum over all of it. Okay. So this is a sum over all configurations that have, in this case, it's going to be n pluses distributed among the minuses. Okay. So for any such state, it turns out to be sufficient to note the following. So if you go take your Hamiltonian and act with it on, okay, what configurations appear? What nearest neighbor configurations appear in each of these states? Well, minus minus certainly appears. And that actually turns out to be the same as plus plus. So you can check, just like for spin half. By the way, spin half xy is integrable because you can do Jordan-Wigner. Spin 1 is not, FYI. So, but the same thing is true. You can't flip-flop if both of your spins are both down or both up. You can't. So this is going to be 0. And then what happens here, if you have a plus and a minus, both plus minus and minus plus get mapped to, and then there is a matrix element that I'm not going to bother, but they both map to 0, 0. So one way to think about it, if you like, is if you're a Hubbard model person. So this plus, you can think of it as a bound state of two particles, like a spin up and a spin down, and then one hops off, and it can hop off to either direction, for example. And then that's what this 0, 0 is. You can think of 0 as like one magnon, so this is two magnons, and then one of the magnons hopped off, or one of the magnons hopped off, and then they're separate again. Okay. So this is an example of a bimagnon decaying into two magnons. Okay. That sounds bad, right? But what's the deal? What happens? So because of this, you can show that if you take any one of these terms and act with it on this, it suffices to consider kind of like term by term what this thing is doing. So somewhere in the sum, there's going to be, and then I'm going to take a configuration and break it up a little bit. So let's say left tensor plus minus tensor right. So what's this? This is just a product state with some configuration of bimagnons on the left and some configuration of bimagnons on the right, and then plus minus in the middle. So this guy appears somewhere. Not a typo. Okay, so I put a minus sign here, and you can convince yourself that these are all equal amplitude, this superposition, but then there's going to be some plus and minus ones, okay? So what happens to this phase factor if I take a magnon and I hop it by one site? Well, I'm increasing one of the r's by 1 and leaving all of the other ones fixed, so this guy becomes a minus. So then I have a minus here, okay? But then what happens when I hit this thing is that this guy becomes left 0, 0, right? And then this guy becomes left 0, 0, right. So these two states are initially different, but they scatter into the same configuration. And they come with opposite signs because of pi magic. Okay. And this happens for every single configuration. And it just cancels out. Okay, yes.
Just to make sure, the catch L, which was a magnon on the left,
Yeah.
it's like minus 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 0.
No, bimagnon. It's and it's any configuration actually. So it's going to be like the total number of bimagnons in this thing has to be n. So there's everybody to the left and everybody to the right. So I'm just saying that for every configuration with a bimagnon on a given site, there is another configuration where that bimagnon is on the next site with everybody else held fixed.
Okay.
And those configurations cancel pairwise. And this feels like a good time to say that this works when the number of sites is even. Because you want an even number of configurations. Yeah.
Thanks.
Okay, any questions about that? No, that's the great thing is that this is term by term. So these are frustration-free states, they're called. So in the sense that there's zero eigenvectors of this Hamiltonian, and they're annihilated by each of these guys. So these are non-commuting terms, but they each annihilate these terms term-wise. Yeah. Yeah. So what happens?
So
please,
just to understand the terminology, you call it frustration free because essentially you can make each term happy separately without disturbing the other terms, right?
Yeah. So like these terms don't commute, but I can write down a state which satisfies each of them.
Okay.
Yeah, that's right. Okay. Any other questions? Okay, but now it's kind of clear like why pi is special. It's special because here I'm getting some destructive interference. So this is essentially an interference effect where all of the channels for your guy to scatter interfere destructively. And therefore, any number of bimagnons you put in, it doesn't decay. Okay, and this is a known mechanism. This has been known for at least 35 years, going back to CN Yang, eta pairing states, which I'll comment on. Again, yeah, not a new thing. There's such a thing as repulsive bound states in Hubbard models where you put in a doublon and then it hops off, but then the interference makes the doublon stable. These are things that happen, and they've been known to happen for a long time. It's just in here, it's a little bit special because you can put any number of them in. Yeah. Okay. All right. So there's a useful property, and I see why I'm definitely not going to get to the end of this today. But it's fine, actually, because I'm going to write down some equations, and then it's all going to just pop out. So there's a property of this stuff that basically, because the whole thing is that these states are supposed to have this property, or these three properties that I kind of advertised at the beginning. And there's a very easy, there's a thing which once you observe it, all of these properties follow immediately. Okay, maybe it's not always obvious, but they follow immediately. Okay, so here's the important thing, or the thing to observe. So these states transform as a spin L/2 representation of SU2. But it's an SU2 that's generated by these guys. So J plus minus is 1/2 sum over I minus 1 to the I S plus I squared. So it's this. Okay, so this is like the raising and lowering operator for these guys. Okay. And then there's JZ, which is just the magnetization. You can check that basically each of these guys has a fixed magnetization because it has a fixed number of bimagnons. And then, as an exercise, you can show that these guys form an SU2 algebra. What does that mean? You show a few things. You show J plus J minus equals 2JZ. And you show JZ J plus minus equals plus or minus J plus minus. So what this is telling you is that the J plus minus acts as a raising operator for JZ. Okay. And then you can show that if you form a vector out of these guys, J dot J, and you act with it on this state, what you get is J times J plus 1 times the state back. And I'll tell you what J is. You can probably guess what it is from what I said in words. And then you can show J plus minus acting on S, X, Y. And it's kind of obvious from the words that I was saying, but like the numbers actually come out the way that you would expect. So you get square root J times J plus 1 minus M times M plus or minus 1. Okay. Times the state back, or N plus, S, X, Y, N plus 1. Okay. So this just means that they transform as an SU2.
There are some plus minus that is missing.
Oh, I'm sure there are. Okay, let's see. Sorry, what do you mean?
I mean, you are acting with J plus minus, and so there must be, I guess, Sn plus minus 1, I guess.
Yeah, plus minus 1. Sorry. There you go. There was only a minus missing. Come on. I gotta finish.
He's gonna write.
J is L over 2. I said it was a spin over L over 2 representation. And what's M? It's N minus L over 2. Yeah. So basically what that means, M is the eigenvalues of JZ. It's the M quantum number. And it's just the magnetization. So you start off and I mean, obviously this guy has a 1/2. So then the vacuum has minus L over 2. And then you just keep raising by 1. Okay. Does that make sense? Great. So using these, you can basically prove all of the things that are special. So one was high overlap with a product state or with a low entanglement state. Yeah. That's a great question. So they don't. And that's important. So that's that's like the thing that distinguishes this from those Magnon states that I wrote down before. So they transform as a representation of this algebra, but these operators don't commute with the Hamiltonian. And that's important because L over 2 is the highest total spin quantum number of this algebra. So if that were the case, then you would just go into like the 0 or pi momentum sector, and then these states would be the unique states in their symmetry sector. So they form a multiplet, but if you go M by M, there's only one state in that sector. And that's actually what happens with C.N. Yang's eta pairing example. Like Yang wrote down these states, but it was because he found this extra SU2 symmetry in the Hubbard model. There was a spin SU2 symmetry, but then Yang found the sort of superconducting analog of this that is in the charge sector of the Hubbard model. And that was the thing that was cool, was that there was this extra SU2 symmetry that people didn't know about before. But then the thing that people call eta pairing states are kind of the unique states in their sector. So those are examples of states that are kind of dictated by symmetry. They're only there because you have that extra symmetry. But here, these are not. They don't commute with the Hamiltonian. And that's kind of the terminological distinction that, turns out to be somewhat important. Yeah. you're, I mean, spoilers. I mean, all kinds of spoilers. So, yeah. So so you can, yeah, I think I'm going to get to this at the beginning of the next lecture, but there's a sense in which basically, like, if you take these operators, why don't I just do it now? But I'll start at the beginning with this again. So if you take like J plus minus and then put a P scar there on either side, what's P scar? It's just sum over n of, it's basically like the projector onto all of the scar states, which is going to be some non-local operator, but nevertheless it exists. You dress this guy with this, and then they do commute with the Hamiltonian. Yeah. That's the upshot. Yeah, so it's not a symmetry, but if you kind of dress it in some non-local way, it is a symmetry. But again, that's just a restatement of, like, these operators are, you know, are good for these states. These states transform nicely under these operators, but the other eigenstates of the Hamiltonian don't. So it's, in a sense, it's a vacuous statement compared to, you know, I mean, it doesn't add anything new.
The variables are some sort of almost right?
Yeah, it's so in this type of model, it's related to a weird conserved quantity rather than an almost. In the PXP, maybe it's an almost conserved quantity. Maybe it's an almost weird conserved quantity. Maybe it's almost integrable. I think people don't quite get it. But here, it's that it's a weird conserved quantity. Yeah.
Well, weird is a conserved quantities for a sub.
Yeah.
For a very small
Only
piece of
for-
the full Hilbert
Exactly,
space.
for a measure zero. But it's also like, it's a conserved, I mean, the fact of being in this sector is also conserved, you know? Yeah. Like the Hamiltonian doesn't mix these scars with everybody else. Yeah, that's right. Okay, great. I think I can get through the properties. So how do you see that these states have high overlap with a product state? So any superposition is fair game. Now, how do I know that I can make a product state by adding these states together? Well, it comes from this nice algebra, because these guys are basically the z-basis eigenstates of the generator of this algebra. Like, so the jz, these are the eigenstates of the jz. But you can show that the following state is the ground is an eigenstate of jx. So take the jx generator, which is, you know, 1/2 j plus j minus. You can show that this state, I'll call it phi 0, which is a product state, is an eigenstate of this guy. It's just plus, you need, I'm with probability 1, I get the sign wrong, but what's a minus sign among friends? So good. So so this state is an eigenstate of jx. And what that means is that it's a particular linear combination of these guys. And the matrix elements are Wigner's D matrix, of course. Right? So it's SU2 stuff. Yeah. I mean, you don't know Wigner's D matrix? Wow.
You're not allowed
No, I'm joking.
You specifically.
You know it. You actually do know it. It's just a name. You actually do know it. Yeah. Yeah. So the point is, this state is a product state, and this is, you know, the lowest weight or highest weight state of the x basis representation of this algebra. And therefore, all of this, if you add up all of the z basis guys with some particular coefficients that have some binomials and stuff, factorials and whatnot, you'll get this, okay? So this fact follows exactly from the algebra, but once you have this, you know, okay, you have high overlap with the product state, great. Then equal energy spacing. Well, we just showed that hxy acting on these states are 0, but if you consider h equals hxy, I guess I had that as a lower index before, but who cares? It's an SU2. So basically, this guy annihilates that tower of states, and then I'm just going to add to that the Z generator. Each of these guys has a different eigenvalue of JZ. So that means that if you add this, the scars have energy En is H n minus L over 2. You just add one of the generators to the Hamiltonian and you split them and it's immediately equally spaced. And then what is the dynamics? Well, then it's really Rabi oscillations of a big collective spin, because it's like you prepare this guy in an X basis eigenstate, and then the only part that the scar states see in your Hamiltonian is this magnetic field. And then they just precess, but they're all kind of precessing together as a big spin. And then entanglement, order log L entanglement. So these states are formally Dicke states. So what does that mean? So, okay. So S, X, Y, N are formally Dicke states. So what are those? Dicke states are the following type of object. So you take, again, I'm not going to worry about normalization, but then remember the thing I just erased? So that was a bad choice. But imagine what I just erased. It was a sum over a bunch of r's, and then there was a -1 to the sum over the r's, and then there was s plus squared. Now I'm going to put sigma plus r1 sigma plus rn. And now this is a spin half system. So I'm going to say all spins down. Okay. So what does this mean? It's an equal amplitude, equal phase superposition of n upspins among L minus n downspins permuted, sum over all permutations. These are famous states. Why are these formally Dicke states? Well, there's as an exercise for you. Like hopefully it's clear why the operator part agrees, right? Because so s plus squared takes a minus and sets it to plus. So what you can think of it is like every spin 1 has a spin half embedded in it that's just the minus plus manifold. And these states just live in that manifold. There's no zero. No zero ever appears in one of these eigenstates. So s plus squared acts as sigma plus on that spin half that lives inside of the spin 1. So s plus squared on site I maps to sigma plus. But then what about those phases? So show that the phases on S, X, Y, N can be removed by a global unitary product over R odd e to the I pi S Z R, and argue, let's call this thing U, argue that U does not change the entanglement. Okay. So you can make this substitution, and then you can get rid of the minus signs with a unitary transformation that does not change the entanglement of the state. So then you've mapped your states to Dickey states, but then it's known that these states have bipartite entanglement entropy of order log little n, log little n. Okay, now, how does that explain the log L? Well, when n is L over 2, right, and actually you should also, this is, you have to be, this is a little bit cavalier. Let's say n less than or equal to, what, L over 4? So what I mean is the entanglement entropy of the Dickey states keeps growing until you get to the equatorial one, which is the middle. Wait, no, it's 0 to L. Sorry, I got confused with the J and the N. L over 2. Sorry. So yeah, the middle one, the equatorial one. Yeah, so the entanglement keeps growing, and then for the ones in the middle where n is of order L, those ones have log entanglement. So actually most of the Dickey states have log L entanglement, except for the ones kind of in the tails of either side. Okay. They also have extensive multipartite entanglement. So the scar states have that too. And that makes them useful for quantum sensing, which is an interesting fact. Great. How much appetite do people have for more stuff? Because I can write down the vacuous statement that I alluded to after Eduardo's question. So I can write down kind of a thing that kind of encompasses this structure. It won't take long, but I'm also fine just writing it at the beginning of next time because it's like fine.
So we need to make a vote.
Yeah.
So students, do you want to?
Yeah, do students want to see that now or at the beginning of the next one?
Who want to see now? Raise the hands.
They want to see it now? Okay, great.
Okay.
Great, perfect. All righty, so, all right. So the formalism that kind of like encompasses this. So what happened here, right? So we talked about it a little bit, right? So I have these states transform as some nice algebra. And if you project the generators of this algebra into the subspace spanned by these states, it's a symmetry of the problem. So yeah. Right. So that means that you can think of this as it's called a restricted spectrum generating algebra, which is, so I got to talk about what a spectrum generating algebra is, but it's not that bad. Yeah, so the question is basically like, how do you get a set of states that have this nice algebraic property, but like, only within that set of states, and then it's not a structure that the Hamiltonian kind of has for every eigenstate, okay? All right, so spectrum generating algebra. What does that mean? So suppose you have a Hamiltonian with an SU2 symmetry. So I'm going to call that HSim. So this is an SU2. I'm just doing SU2 as an example. You can do more fancy things if you want. But SU2 is kind of easier. And then you add a term to it. Okay. Now, HSim is an SU2 symmetric thing. So this would be HSim commutes with JZ. And now J is like some abstract SU2 symmetry. So all of the SU2 generators commute with HSim, right? But then there's this extra part, HSG, stands for spectrum generating, which obey, the commutator with J plus minus is equal to plus or minus omega J plus minus. Okay. Yeah. So what that means then is that for this guy, the commutator of H with HJ plus minus is again plus or minus omega J plus minus. So if your whole Hamiltonian has this property, like any SU2 symmetric Hamiltonian, and then you add a magnetic field in the z direction, say, to it, your spectrum is going to respond. Your spectrum was originally in degenerate multiplets, and then the multiplets are getting split, right? So that's what we say. That's essentially what this is. Okay. So the thing that's different here is that this Hamiltonian does not have a spectrum generating algebra in the sense that we had HSG in our spin 1 XY. Okay, that was a Z field. But then it turns out that if you take J plus minus and commute them with the XY model, so if you take HXY and commute with J plus minus, that's not 0. Okay, so HXY annihilates the scar states, but it's not symmetric under the SU2. Okay, so that led people to defining this thing called a restricted SGA, and then this terminology came from this paper. So I'm going to give you the actual reference because I'm not going to prove the conditions. But yeah, so and this is PRB 102 085140 2020. And I say this because there are multiple good Sanjay papers from 2020. So, I want to be specific. Okay, so what they did in this paper, one of the things they did was they proved sort of a theorem. So let me phrase it as a theorem. So given a state psi 0 such that, basically that's an eigenstate of the Hamiltonian. So H psi 0 equals E0 psi 0. Okay. And an operator J plus satisfying the following conditions. So 1, H commutator with J plus. This is an operator. And when that operator acts on psi 0, you want to get omega J plus psi 0 back. So a way of saying that is basically like, okay, who cares what this commutator is as an operator, but like whatever that operator is should sort of have this property. Okay, so I'm not making a statement about the algebra of the operator. I'm making a statement about what the commutator does when it acts on a specific state. So I'm thinking about taking this algebra and projecting it onto one state. Okay, and there's another property, which is that the double commutator as an operator should be 0. Okay, then there exists a set of states, psi n equals j plus to the n psi n with
Psi 0, I guess. So psi n.
well n yeah,
Okay.
thank you. I said my hand and my mouth are not connected. Okay, good. So h psi n equals e naught plus n omega psi n, or psi n equals 0. Because like eventually you just take this operator and you keep hitting it on psi 0 and eventually it's 0, right? So what this is saying is basically, okay, what do I need in order to get something like what happened in, spin 1xy, or, prior to that, there was the AKLT, right? This is all kind of similar. Actually, to get AKLT to fit into this framework, they had to define something called a restricted SGA of order M, which is even some more stuff, but I'm not gonna get into that. But essentially, there has to be a state which gets acted on nicely by this operator. And then it turns out this guy, if you look in the proof is in Appendix C of this paper. But it turns out that the proof is, as many proofs are, is by induction. And this is like what you need to do the inductive step. Yeah, so, okay, good. This is a restricted SGA. Great. Now, I want to make a couple of comments. This is a sufficient criterion for getting the kind of thing that I showed. Nobody knows what if or what are the necessary conditions. Nobody knows. Okay? So this is a statement like if you have this stuff, you get those states. Okay? That doesn't mean that this is the only way. For example, this thing as an operator equals 0. You probably don't quite need, this is a lot to ask, right? Like this is, this is a lot to ask of this operator. You could say this thing equals 0. You could have some M states, some set of states that this thing actually annihilates or something. And that's actually what the order M RSGA is. So I'm just trying to say like, this is just one thing, one way that this can happen. And the thing that's appealing about it is that all you need is basically, this would be like the vacuum in your tower of the XY, the polarized state. But then, you take this raising operator and then you show this and then, you show this and you can show for yourself as an exercise that this indeed is true for the spin 1xy. But yeah, this is, it's sufficient, but it's not necessary, and we don't have necessary conditions for scarring. Optimism. Go find them. But yeah, so, okay, that's it. Yeah, that's all that I wanted to say today, actually. So, great.
More?
Questions? Yeah.
So how much does an SZ term spoil all this story? You mentioned
Totally.
AKLT and
Completely.
completely what?
Spoils it.
Destroys.
Yeah, absolutely. I mean, you can do things like compute the energy variance in these states when you add the SZ term. So this is all fine-tuned. And generally, in order to satisfy these things, yeah, it's going to be fine-tuned. Adding an SZSZ, if it's small, you can do things and look at like how the fidelity of these states decays or how the revivals decay. You can do some Fermi-Golden rule and try to figure out the time
Yeah, because
scale.
the AKLT state is sort of connected to the Heisenberg limit
Yeah.
in terms of
Yeah, so this is not, that's the thing. It's not a statement about ground state. It's a statement about these special excited states that are of this form. Now, there's other stuff you can add where these states remain eigenstates. So for example, so what you just said is bad, right? But single ion anisotropy is okay. Why is this okay? Part of the structure of these states is that it's only the minus or the plus, the zero never enters. And this term only distinguishes plus minus from zero. So those terms happen to be eigenstates of this. What's another thing that's okay is, not J, oh, J. Who would write J? Come on, guys. Okay, good. S plus I, S minus I plus 2k plus 1, any odd number, plus Hermitian conjugate. So odd neighbor flip-flops are okay. Why? It's the destructive interference. So hopping by one site is okay. Hopping by 2 sites, you get frustrated, it turns out. Hopping by 3 sites is it? Yeah, exactly. So and that is basically, so I mentioned bipartite graphs. So the graph remains bipart, the 1D chain, the Hamiltonian sort of action on that, right? It's sort of, this is, if you divide the chain into sublattice A and B, you only want hoppings that connect A to B. You don't want hoppings that connect A to A. So it's like, chiral symmetry or whatever you want to call it. So any bipartite graph, that turns out to be okay, because the point is that if you have somebody on an A or a B site, you'll hop onto some onto some A and A and A, then you hop to, yeah. Sorry. But yeah, so that's also, so there are terms that you can add, and it doesn't matter like what the coefficient of this term is. It doesn't matter what the coefficient of this term is. All of the properties are preserved. So
students.
Yeah.
Okay, so let's give preference to students.
So I'm just trying to think of some maybe intuition of this. So you have this full Hamiltonian, the XY model, and there's this subspace which kind of obeys this symmetry of like a spin half.
yeah.
And on this subspace there are the eigenstates which would be our scars.
Yeah, I mean, it's basically you have if you like, a set of states that are defined as like the largest spin representation of this algebra. And then, because these guys do that, you get these eigenstates. That's one way of, they are eigenstates. Yeah. Another way that you can think about it is like, so if you want to take this, if you want to go from here, which has a regular spectrum generating algebra, to something that has scars, you can add any term that annihilates all of the states that are in a particular representation of this thing. And it turns out that the spin 1xy, it annihilates the scars, but it's actually like it's a sum of a term that's symmetric under the SU2 and an extra term that's not, but it annihilates. That's done in a paper by Daniel Mark.
So
And yeah.
I think that the two things put together in such a nice form with this.
Yeah. And let me say one other thing actually while we're still talking, is that there was these SN XY states that are proportional to J plus to the N acting on this polarized state. The AKLT one, SN AKLT, which came first? Is the same J plus, actually. Same operator, acting on the AKLT ground state, which if somebody asks me what that is, I can tell you. But it's actually like you take that famous spin model, you take this same operator, and you hit it on a different state, and it generates, again, a tower of states. Now, how did we come up with this? We wanted to see how the revivals come from this, because we didn't understand. And then at a certain point, we were like, I give up. What if you just hit it on the polarized state? You get these states. Is there a model that has these as eigenstates? And then spin 1xy did. So these are just kind of, in a way, they're related. And there's a concrete way that the models are related, actually. But then it's like, OK, well, what's the initial state that you should choose? OK, and actually, you could put this here as like a corollary to this theorem, is that e to the alpha j plus, so a coherent state of these bimagnons, or whatever your j plus excitations are, acting on psi 0, has revivals. So that's, yeah, so generally speaking, yeah, it's like you have special excitations that are made by these guys, and then any coherent state of those guys will exhibit. Other states will too, but like one nice one that you can write down that projects onto everybody is a coherent state. And you can do this for AKLT, no problem. It's just, not necessarily immediately obvious that that's what you want to do.
Just another question about the jig state you wrote, which was on like the spin half representation. Yeah. Shouldn't it be like anti-symmetric on like, isn't there any -1 to the I?
No, there's not. They're as defined. They do not have a minus sign there. So the point is that the states that I wrote down, which do have the minus signs, if you do a rotation that I wrote down, the product, you can get rid of those signs. And that rotation, because it's a product operator, it doesn't generate or remove any entanglement. It doesn't change the entanglement. So that's the thing, is that you can do a unitary transformation that preserves the entanglement and gets rid of the phases. So the phases turn out to be not so important. Okay. Now, if you wanted to do that for the model, right, the model is translation invariant, right? But the states have this -1. If you wanted the states with no -1 to be eigenstates, then you would transform the Hamiltonian, and then your Hamiltonian would become staggered. So you can stagger the Hamiltonian, or you can stagger the states.
Okay.
Yeah.
Thanks.
Maybe one naive question, very probably technical. Like in this, as it's written now in the theorem, the second condition is not satisfied on the central whiteboard, right?
Maybe for which one? Sorry, here?
So second condition, H, double commutator of H J plus equal to 0 is not satisfied on the central whiteboard, right? Yes, because the last line is not commuted. Like if I just consider the first commutator, H J plus minus, if I compute it with H, is again J plus minus. Is it just a misprint there, or it's just?
No, I think this is right. I think this is like just something that you need in order to complete the induction on top of this thing.
But it seems that you need to complete the induction, not the second commutator with H, but with J plus. No. It's a minor thing.
J plus.
Because this is what you will raise to the power n.
Maybe. No, I don't. I mean, unless maybe I was copying wrong.
Okay.
But I think, no, I mean, so yeah, I mean, in the proof, what they kind of do is they define these HNs, which are like first commutator of H with this thing. And then there's H, and then, so they define these HNs to do the proof, which are n-fold commutators of H with J plus. So I assume H2 equals 0 is a condition of the proof, if I recall correctly.
But then this is not satisfied here.
yeah.
But this
It's not-
he was understood. He was saying that condition 2 is can be in many cases an overkill.
Yeah, but it's like
Yeah, yeah,
it's not. So is it an overkill here? This is my question.
Is it an overkill here?
Because that's not satisfied.
Yeah, probably in this case, in this particular case, it's an overkill.
I mean, let's look.
Maybe a
We'll
physical
see.
question, maybe a short physical
Yeah.
question. This PXP model is just adjacency matrix on a certain graph.
Yeah.
Right? Because it's constraint model. Do you have something like that here?
I mean, of course. Yeah. You take HXY, I mean, it's HXY is just a matrix that has constant. It's a matrix of ones and zeros properly. If you scale this stuff properly, it's a matrix of ones. Well, I guess it's not exactly because you have square roots of square root of 2 and stuff. So it's a weighted graph, but it's a graph. And actually what you get here is an example of this like Aronoff-Bohm caging. For some reason, there's been a bunch of papers about this recently. But it's basically like, the graph has a shape such that if you populate certain nodes of the graph and then hit the Hamiltonian on it, you scatter onto nodes. And if you put pluses and minuses around in the right way, it all interferes. Yeah. So you can view this as like Aronoff-Bohm caging on a graph. Yeah.
Okay, now, in principle, the next talk is supposed to start in 4 minutes. So let's take a break up to 4:45, but then let's start sharp because they will kick us out soon. So yeah.
Sorry. Yeah.